Hello and welcome to another lecture of classical motion of a single particle. In this lecture, we simply continue our previous discussion on non-inertial frames of reference. So, in the last lecture, we discussed Galilean transformation and also how one cannot match F external is equal to MA for a non-inertial frame of reference. And we also showed the requirement or the necessity of introducing a pseudo force. So, a pseudo force, once again for recapitulation, is a force which with respect to an inertial frame of reference does not exist. Okay. But the pseudo force has to be introduced in order to make the Newton's law to be valid, Newton's second law to be valid, or actually Newton's first two laws, first and second laws to be valid in a non-inertial frame of reference. Okay. So, that finally, when an inertial frame of reference talks to a non-inertial frame of reference, they agree about the motion of a particle which they are studying. Okay. Because fundamentally, we have to understand that this all are done in order to make sure that the laws of physics are the same in all reference frames. That is exactly our dream. If the laws of physics are not same in all the reference frames, then actually the physics would be complicated and you cannot just bind the whole physics just by some set of universal laws. Then you have to make system specific laws which are quite complicated, that we do not want. Okay. Then we also introduce the case of uniformly accelerated frames, where we showed that the space and time coordinates, they are simply related just like the case of a uniform acceleration. And I also gave you two examples, one for a non-inertial frame of reference, okay, having vertical acceleration, and another of a non-inertial frame of reference with horizontal acceleration. Okay. I think you have already thought about the pendulum problem in the train. If you have already thought and if you have found the answer, you just let me know in the forum discussion. So, now coming to this rotating frame of reference. So, we know that whenever a particle is rotating or is performing a rotational motion, the particle is also experiencing an acceleration. Okay. Now, depending on that under which force field it is rotating, okay, the nature of the acceleration can be different. Okay. So, for example, you know that whenever we are just talking of a central force which is radially acting, then when a particle is just rotating in a circular orbit, very simply the simplest case possible, okay, of rotation, then you know that the only acceleration we have already discussed which is coming into play is the centripetal acceleration, okay, which is radially inward. Okay. Now, here we will just see that since rotational frames of reference are also non-inertial frames of reference, so what will be the relation between the kinematics and the dynamics in a frame of reference which is inertial and a frame of reference which is rotating with respect to the first one which is inertial. Okay. For simplicity, we also assume that at the very initial time instant, okay, the origin of the two frames of reference, they coincide. So, you can now think of two frames of reference. One is given by this x, y, z, which is the unprimed one. Here you can see this one, the coordinate system drawn in black. Another one, the coordinate system which is sharing the same origin, but with the primes as their axis. So, this is x prime, y prime and z prime drawn in the light brown color. And here you can actually see that this type of coordinate axis, okay, this primed system, this is actually rotating with respect to the unprimed system. If an observer who is measuring some displacement, some velocity, okay, some acceleration in this primed frame, and the same things are measured with respect to some observer in the unprimed frame, then what will be their relation, that we will discuss in today's lecture. So, for that we first try to write that let us take an arbitrary vector C, okay. And I will first say that C in the unprimed frame, it can be written as Cx I cap plus Cy j cap plus Cz k cap. In the primed frame, the same vector can be written as Cx prime I prime cap plus Cy prime j prime cap plus Cz prime k prime cap. Okay. Here there is a point of caution. In this unprimed frame, this y direction, x direction and z direction, they are constant in time, whereas in this prime frame, this x prime direction, y prime direction and z prime direction, they are changing and they are rotating, okay, with respect to some direction in cap, which we will see afterwards, okay, in time, okay, and that is why they are not fixed. So, this I cap, j cap and k cap with primes, okay. So, I cap prime, so this I cap prime, j cap prime and k cap prime, they are actually changing with time, okay. Now, we have to find the ddt, because any motion in mechanics comes with some ddt, okay. So, if I say that ddt of C in the inertial frame is given by this quantity, and ddt of C vector in the rotating frame is given by this quantity, okay. Then how to connect between them? So, of course, I know that ddt of this thing, so I know that this will simply be in inertial frame. I can write the expression completely, and I know these are independent of time. So, I will simply have dcx dt I cap plus dcy dt j cap plus dcz dt k cap, okay. But I also know that this C vector is also equal to this, and the time in both the frames of reference, they are equivalent, okay. And that is why I can also say that this dc dt is also equal to ddt of Cx prime I cap prime plus Cy prime k prime plus Cz prime k cap prime, okay. You can ask me, this is an expression in the prime frame, why I write that? This is an expression for the whole vector, which is also true in the unprimed frame as well, when you write the whole vector. What is the difference between the primed and unprimed frame is that with respect to the unprimed frame, these things changes with time, and with respect to the primed frame, because the primed observer itself, since it is rotating, cannot see the change of the direction of the unit vector. So, with respect to the primed frame observer, this will act as constant, okay. But in an unprimed frame, they are changing with time. So, I can write this is equal to ddt of Cx prime I cap prime plus Cx ddt of I cap prime plus ddt of Cy prime j cap prime plus Cy prime ddt of j cap prime, and finally plus ddt of Cz prime k cap prime plus Cz prime d dt of k cap prime. Okay. Now, these three things where you just consider that d dt is just acting on this Cx prime, Cy prime and Cz prime, but not on the unit vectors. You can combine these three and you can claim these are equal to d dt of C in the rotational frame, that you can do. But because with respect to the rotational frame, d dt of I cap prime and d dt of j cap prime and d dt of k cap prime all are 0. Okay. But somehow with respect to inertial frame they are non-zero. So, I write them Cx d dt of I cap prime plus Cy d dt of j cap prime plus Cz d dt of k cap prime. Okay. So, now the main point is that in order to relate these two, this inertial to this, so I can write actually dc dt inertial. Okay. In order to relate these two, you have to evaluate this one, and for that you have to find the unit, you have to find the d dt of the unit vectors in the rotation, in the rotational frame of reference. But there is a good news that these unit vectors are always unit vectors, that means they are the vectors of constant magnitude, and that is 1. Okay. If we can find the law for d dt of a vector of constant magnitude, but it is rotating with some arbitrary direction, that direction can be or cannot be fixed in time, okay, then we are done. So, for that we will use this figure, and where we can show that, okay, so this is the origin O and I have a vector B which is having always a fixed magnitude, and if the vector B is rotating with respect to some axis with direction n cap, then it will actually precess by describing a circle like that, and the whole surface will be a conical type of surface, as you can easily understand. Okay. So, this is called a precession type of motion, where the tip of the vector actually is describing a circle always making some angle with respect to the vertical, and we call that angle to be alpha. Okay. So, here what is the direction of this rotation? Let us say if the point here is rotating in this plane, then we can say that this is actually a rotational motion in this plane, and this is a 2D motion of course, and then this is nothing but, so the direction perpendicular to that plane is nothing but the direction of the corresponding omega, where omega is nothing but d dt of phi, where phi is the, so phi is the azimuthal angle. Okay. So, if this is true, then how to find the d dt of this vector? Okay. So, for that what we will actually do is the following. We first calculate, so we have to calculate dB dt, okay, that we do not know, okay. But for that we first have to calculate the incremental vector dB. So, you see, if at time t is equal to t, the B vector is here at this point with, the tip of the B vector is here, and at time t plus delta t the B vector is here at this point, then this vector which I am trying to join will be, so if delta t is very small, this will be almost a straight line, this is now exaggerated here, and it will give you delta B. Okay. So, now you actually will have also like a vector addition, B plus delta B will be equal to B plus delta B, by which will be represented by this this vector, this one. Okay. Now, this is also equal to the arc subtended by this angle. Okay. So, if I can say that the azimuthal angle subtended is small, so it is d phi. So, we can also say that this radius of this circle times d phi will be exactly equal to this arc. That is exactly the S is equal to r theta formula, you all know, right. So, and then what is the radius of this thing? So, if this is mod b and this is alpha, this radius will simply be b sin alpha, okay, because this is the perpendicular angle, okay, and this is base. So, this is the perpendicular and this is the hypotenuse, and that is why you have this angle to be alpha. So, you have this thing to be b sin alpha. So, I can actually write delta b mod is equal to b sin alpha times delta, so b sin alpha times delta phi, that much I can write. Now, delta phi, from this definition I can also say this is nothing but b sin alpha omega delta t. Okay. If I have this, then actually you can have delta b by delta t, which will be equal to simply b sin alpha omega, b sin alpha omega. Now, you see, if I say this is the vector v and this is the direction which I attribute also for omega, that we know, because if this is the tip of the vector b is actually moving in a circle, and due to the rotation of that tip actually there is an omega vector which is developed over here, and that is why you say that b sin alpha omega is nothing but the mod of b cross omega or omega cross b. Okay. So, if you now simply say that okay, I am taking the limit delta t tends to 0. So, then actually I will have dB dt mod will be equal to b cross omega mod. Okay. Now, what will be the direction of dB dt? So, b direction is in this direction tangentially, and you will actually see that if you do omega cross b, so that will actually, if you then say that this is the direction of b, so you just extrapolate this thing over here, this is the direction of b. If you do omega cross b, then only according to right hand corkscrew rule your particle will move in this direction, the tip of the vector b will move in this direction, and you can actually say okay, then my dB dt is actually omega cross b. Okay. Now, this is true for any vector of constant magnitude which is moving with respect to some, which is rotating, whose tip is rotating with respect to some arbitrary direction. So, if I now say this is the same case here, where this primed coordinate, all the directions of this prime coordinate system is actually moving with some arbitrary direction omega, I mean arbitrary direction omega cap, or with respect to some arbitrary vector omega, I do not know what that is, but now actually I know that omega is the angular velocity of the corresponding to the rotation of the tip of the vector of the constant magnitude. So, I can actually use this theorem, I mean this conclusion, okay, this result for all the I cap prime, j cap prime and k cap prime, and I can say that prime, I can say that I have, so d I cap prime dt will be equal to omega cross I cap prime d j cap prime dt will be equal to omega cross j cap prime. Okay. And then I actually say that this is correct, and d k cap prime dt will be also equal to omega cross k cap prime. Okay. If I now put all these things in this expression, you will have dc dt inertial will be equal to dc dt rotational plus, so Cx, I think they should be Cx prime, right? That is a, yeah, yes, Cx prime, correct. Yes. So, can actually write Cx prime times omega cross I like this plus Cy prime omega cross j cap prime plus Cz prime omega cross k cap prime, and you have dc dt rot will be plus, so Cx prime I cap prime plus Cy prime j cap prime plus Cz prime k cap prime is C, so you will simply have omega cross C. Okay. So, you see that the relation between the ddt of any vector in inertial frame is nothing but equal to the ddt of that vector in the rotating frame plus omega cross C, and the direction of this omega, or and the meaning of this omega is the angular velocity corresponding to the rotation of the tip of the vectors or the tip of the unit vectors of that rotating frame of reference. Okay. If you have this, then you have a very powerful result here. I write that. So, for any arbitrary vector dc dt, inertial is equal to dc dt rot plus omega cross C. So, this result can be used to relate different mechanical quantities like velocity, angular momentum, okay, acceleration, okay, in an inertial frame of reference and a rotating frame of reference. Just 2 or 3 interesting points here. You see that if you take, for example, instead of C, you just take the position vector r itself. So, what it will give you, dr dt inertial, I just write I for inertial, is equal to dr dt rotational plus omega cross r. Okay. So, that is the extra term you have to add in order to, you have to add with respect to this in order to have dr dt with respect to an inertial frame of reference. You can do the same thing with a velocity here. So, then it will have a velocity and velocity here as well. Okay. Very interestingly, you can also observe, if it is instead of C, I write omega, what happens? I write then ddt of omega in inertial frame will be equal to d omega dt in the rotational frame plus omega cross omega, which is 0. So, if C is omega vector itself, then we know that dc dt inertial is equal to dc dt rotation. So, if we have a vector which is omega or a vector proportional to omega, okay, that lambda can be constant, cannot be constant. If it is just proportional to omega, proportional to omega, okay, then your omega cross this vector would vanish, sorry, this vector would vanish, and you will have always this thing. Okay. So, finally, I can actually write. So, I have already seen that. So, we know dr dt inertial is equal to dr dt rotational plus omega cross r. We can now say, we can go one step further and say, okay, what about this dv dt inertial? So, that will then be dv dt rotational plus omega cross v. Okay. Now, I can use this formula as v will be equal to, so I can somehow choose to call this thing as v prime, okay, if you want, or v rot maybe, because primes can be, yeah, v rot, okay, plus omega cross r, okay. And here whenever I write this thing, I actually can say, okay, so d dt of v in the inertial will now be equal to d dt of v rot plus omega cross r, okay, rot plus omega cross v rot plus omega cross r. Okay. So, I can see that the ddt of v inertial, that is the acceleration in the inertial frame, will be equal to exactly the sum of these two terms. So, I can now write A in the inertial frame will be actually equal to ddt of v rot in rot, okay, plus I have ddt of this quantity, omega need not be constant. So, I can actually write, so one thing can be omega cross dr dt rot plus d omega dt rot, okay, cross r, yeah, plus omega cross v rot plus omega cross r. Okay. Now, you see here I have several interesting things. So, this one is the acceleration measured in the rotational frame. So, I can write this as A rot, okay. I can write that as A rot, plus this term I can say, okay, this is omega cross v rot. There is another omega cross v rot. So, I can actually have 2 times omega cross v rot, okay, plus I have d omega. So, I can say that this is yeah, d omega dt rot cross r, okay, plus finally I will have omega cross r, okay. Now, like this, okay. Now, I want to express, so I know for this one this will be equal to, so if you just multiply this with the mass, then you will simply have the external force, but if you multiply m with this, you will not equal to the external force, but for that what is necessary is that you have to subtract the whole thing from this A inertial, then you will have something, okay. Once again, so if I just write that A rotational, okay, so that will be equal to A inertial minus 2 omega cross V rotational, okay, minus, let me just check, so omega cross r d omega dt rod, yes, okay, so d omega dt rod cross r minus omega cross r, okay. So now you see that you can now say, okay, so the acceleration which is actually seen by the rotating frame will be exactly equal to the acceleration seen by the inertial frame of reference minus all these things, and these things are only coming because I also need to make Newton's second law valid in this rotational frame of reference, okay. So once again try to understand that just m times this one does not give you f external, but if you do m times A rotation plus all this thing, then you will have actually equal to m times A inertial, and that will be actually equal to the f external, okay. So this whole part is the part of the pseudo force here. This one is known as Euler force, and many a times Euler force, and many a times this is not taken into account because we consider the case of a uniformly rotating frame of reference where omega is constant and ddt of omega vanishes, okay. This is known as Euler force. This is known as Coriolis force. Coriolis force, okay. This is non-zero when V rotation is non-zero. That means a particle which is having some velocity, non-zero velocity with respect to the observer in the rotating frame of reference, then only this term comes into play. So on earth, I am sitting on the surface of earth, and the earth center is just like me, is actually rotating with respect to the sun, okay, around the sun. Now with respect to that specific motion, me and the earth center, they are performing exactly the same motion. So we do not have any other relative motion, okay. If I just sit on the surface of the earth, then I do not have any relative motion with respect to the earth center, and then only I will have a 0 V rot, okay, with respect to the earth center, and that is why the Coriolis force will not act on me. But if I now start walking on the surface of the earth, that means the earth is rotating, with respect to that I will have some movement, but also in addition to that with respect to the earth center also I am now moving, I am now walking on the surface of the earth, and then there will be some non-zero V rot which is coming, and I will experience a Coriolis force. The final thing is this one, it is called a centrifugal force, okay. All these things are actually acceleration. To be very honest, I have to write, to make them force, I just have to write m everywhere. So yeah, then that would be technically correct, m and this, yeah, now they are all forces, yeah. So you see that this is a centrifugal force, and the centrifugal force is actually also acting even when you have no relative motion with respect to the center of the earth, for example. So even if the particle is not moving in the with respect to the center of the rotating frame of reference, the particle will still experience a centrifugal force because there is a global motion of rotation, okay. Two things, this one, okay, is actually cross product of omega and V rot, and that is why this is, so with respect to this non-inertial or the rotating frame of reference, this is a no work force, because anything which is any force which is having a cross product with the velocity has 0 power, because if you do the force dot V, that will give you 0. So, this is exactly the same case as that of the Lorentz magnetic force, okay, where you had a force which is like V cross B. Here this is actually, if you take the plus sign, V rot cross omega. Okay. The second thing is that both this thing and this thing, if you do dot omega with this and this, okay, both of them would vanish. So, that is why this another important conclusion is that both centrifugal force and Coriolis force, they are actually perpendicular to the plane, to the direction of the omega. Okay. So, in the discussion of motion of different celestial bodies and also terrestrial bodies, this knowledge is very, very important for us, because our earth is a rotating frame of reference and it is moving with respect to the sun, it is also spinning. So, we can actually, whenever we try to discuss, for example, the motion of river, the motion of air, the motion of wind flow, the motion of some comet, some satellite, we always have to think of the pseudo forces. Okay. So, just to tell you that you also understand that whenever the wind is flowing from one part to the other part on earth, since it has a non-zero relative motion with respect to the earth center, it actually also experiences a Coriolis force. Okay. So, this type of things will be very, very important for the study of geophysics and the geoscientists as well. Okay. Thank you very much.